This short introductory video will go through the basics behind the technology of the Videometer Lab and some examples of use cases. The video is intended to give new users the necessary basis information and an introduction to the Videometer Lab and its software before beginning the 4 training modules. The Videometer Lab device is Videometer's flagship instrument for multispectral image acquisition. Together with the leading-edge Videometer Lab software, it is used for both exploratory analysis, for calibration model construction, and for routine quality control in a wide range of application areas. Among others, food and feed, agriculture, pharmaceuticals, medical devices, microbiology, textiles, materials, cultural heritage, and more. And now to the $1 million question: what is multispectral imaging? And how does the Videometer Lab use these multispectral images to classify and quantify different samples and objects? As a new user of the Videometer Lab, you will, by watching this video, get the necessary theoretical basis for understanding what goes on in the Videometer Lab when it takes images, and why the images of your samples turn out as they do. Further, this video will also give you the tools for coming up with new ideas to how the Videometer Lab might help you analyze your samples based on the possibilities that comes with multispectral imaging. In the end of the video, we will briefly go through the content of the 4 training modules which comes with the Videometer Lab and what you can expect to learn in these modules. So, what is multispectral imaging? A multispectral image is essentially a set of images combined into one image. This set of images is taken immediately after each other in a sequence. But what is special with this set of images is that each one of them is taken with a distinct wavelength. As it is illustrated in the figure to the right, we have this stack of images taken at different wavelengths. In one Videometer image, we have 19 images stacked on top of each other. These 19 layers are called bands. So one image has 19 bands. These 19 bands are taken both in the visible and non-visible light spectrum. The non-visible light consists of UV and near-infrared light, called NIR. There is 1 UV band and 5 NIR bands in a Videometer image. The visible light is the classical color spectrum as we know it, and we have divided it into 12 different colors, ranging from violet to red light. But why even divide the light into all of these bands? What is the point of it? So, when you take an image with your camera or phone outside in the sun, your surroundings are illuminated with what is called white light, which essentially is all of the visible wavelengths seen at the same time. What we do here at Videometer is that we simply, figuratively speaking, split up the white light into all of its components, as it is illustrated with this classical prism figure. Eventually, the information in the single image that is taken with white light will be the same as the information in all of the single color images if you combine them. But this separation of the image into several sub-images enables us to do more specialized analysis on our samples. Because when we split up the white light into separate wavelengths, we visualize how different colors interact with the samples one at a time. What is meant by colors interact with the sample is that, as we know, light is made up of waves with different frequencies, and all physical things in the world are made up of atoms with different chemical properties. These different chemical properties are what makes you see the grass as green and apples as red. So, depending on which wavelengths, and thus frequency, interact with an object, the object will reflect a certain amount of light, which will be captured by the camera. The wider the object seems in the image, the more light is reflected from it. As it is seen here on the slide, we have an image of some vegetables of different colors. Below is seen 4 bands taken with different wavelengths. The first band is taken with UV light. What is noticeable in the UV band is the amount of details which becomes visible in the lemon and garlic pieces. When looking at the green band, we see that the lighter colors, white and yellow, are more distinct. Whereas in the red band, the red and orange vegetables now also lights up. In the near band, even the very dark eggplant becomes white, and the grape and lemon almost seem see-through here. So, from this small example, it is obvious that dependent on the type of light, different sample characteristics becomes apparent. An extra small example is seen here of a biscuit, where somebody by accident has spilled some water on it. In the near band, this moist area becomes very distinct. What is special for near light is that it to a higher degree is absorbed by liquid. This makes it ideal for moisture detection, which the biscuit is a perfect example of. But this is just one cool example, and you would be surprised how many things is actually possible to see with multispectral light, which cannot be seen by the eye. Here is seen all the 19 bands for one image of a sample of oilseed rape with that mixture. From these images, it is clear how the wavelengths interact differently with distinct objects in the sample. Now, moving on to how the Videometer Lab then captures these multispectral images. Here is seen an illustration of how the Videometer Lab roughly looks like on the inside. Under the top of the black hat is placed the camera. Around the equator of the dome is placed small LEDs, which emits the different colored light. There is a reason for the spherical ball shape of the Videometer Lab device. The perfectly spherical dome ensures complete diffusion of the light that is emitted from the equator of the sphere. Perfectly diffused light is essential in order to illuminate the samples under the dome, which in the end will result in the best possible images of very high quality. Once you then turn on the Videometer Lab, you will see that it flashes different colored light in a sequential manner. One series of a color set corresponds to one image. So to sum up the Videometer spectral imaging technology, it is a combination of machine learning and AI combined with spectroscopy and imaging. These technologies combined is known under many names, among others spectral imaging and image spectroscopy. It is ideal for heterogeneous samples and for analyzing sample chemistry in a non-destructive manner. How is all of this technology then put to use? To illustrate this, we will be going through some use cases focusing on different methods. We will start with the classification example. Here we have two different kinds of seeds, which look very much alike. We will use the multispectral color differences in the images to create a method which can tell these two seed types apart. We call this the spectral fingerprint of the sample. We start by defining two classes, a class for each type of seed. Then the software conducts a so-called transformation, which essentially is a multivariate machine learning classification method made easy and user-friendly with the Videometer Lab software. This method creates new images where color differences in the images define which class the seeds are predicted to belong to. How likely a seed is to belong to a defined class will be visualized by the class color it is given in the new image. If you then mix a sample with the two types of seed, you can get a result looking like this. Here, the true class the individual seed belongs to can then be determined by the average class color in each seed. This is all done using the Durham spectral fingerprint from the sample. The next classification example is not based on color, but on size and shape. Here we have two different types of rice. Each rice type is given a class color, and each rice is then imported into our blob tool as separate small image objects. The blob tool uses classification trees and machine learning to solve classification problems. In the blob tool, each small rice will have a color and label indicating what type of rice it is. In the blob tool, it is possible to plot different features from the small rice objects. In the histogram is seen the distribution of rice width depending on which type of rice it is. This width feature could, for example, be used to make a classifier which can tell the two types of rice apart. The information can also be visualized in a 2D scatter plot. Here both the width and how circular the individual rice is used to plot the information. The combination of the width and circularity can also be used to make a distinction. So, in the end of the day, a classifier for separating the two types of rice might be made up of several combinations of features like these two examples. And then it will be able to classify them into two groups. Next up is a croissant example. Here we want to visualize and quantify moisture in the croissant. So we need to detect the moisture, but in the regular color image, no moisture is really visible. In order to detect this moisture, we start by removing the background and the holes in the croissant. Then we define two classes again, a dry and moist spread class. And using the spectral fingerprint of the sample, we can detect these moist areas in the bread. But in addition to detecting the moisture, these results could also have been used to estimate the size and number of pores in the bread. Now moving on to a quite different example. Here we are dealing with some white powder. At first, the powder seems very homogeneous. But if we perform a noise analysis on the image with the Videometer Lab software, we will be able to exploit some details in the sample which at first is not immediately visible for the eye. We perform the noise analysis and look at some close-up images of the sample. From the analysis, the result is a set of images describing different features in the sampled image. First, we get an image that visualizes the texture in the sample. The next image focuses on visualizing spectral differences in the powder ingredients, here seen as black and white. Next, it also identifies impurities, thus objects which are completely different from the main sample. The last example will show how the Videometer Lab can detect fluorescence in plants. Here we have an image of some seaweed in various conditions. The fluorescence in these images have been detected using a light filter called a filter changer, which is an add-on to the device. The first image example shows UV fluorescence in the seaweed, and the second image chlorophyll fluorescence. So, to sum up the essence from all of the examples that we have just gone through, when you do multispectral imaging with the Videometer Lab, you will be capable of making classification among samples which looks alike, based on color, size, shape, etc., measure color intensities, detect surface irregularities and characteristics, finding impurities in samples, and the list goes on. Eventually, the Videometer Lab and software is so flexible and extensive that it can be programmed to model an endless list of applications. When you have received your Videometer Lab, you are ready to start the 4 Videometer Academy training modules. The training modules will teach you how to set up and operate the Videometer Lab device and software. There are 4 training modules, each of 2 hours. If needed, help with setting up the instrument will be provided during the first training module. After the installation, the training modules will go through the functionalities and toolboxes included in your instrument license. For the modules, you are more than welcome to bring and use your own samples for the training. To get more information on the Videometer training modules, log on to our webpage and log in with your credentials. Under Videometer Academy, a more detailed content description of the training modules is found.